we have here, what is the Lewis structure for H2PO4? And if necessary, expand the octet on the appropriate atoms to lower formal charge. So with this, the way I like to solve these questions is I actually like to solve what the and it's interesting here because they use H2PO4 because typically Lewis structure of H2PO4, because if we actually were to try to separate it by the ions, the cations and the ions, you'd first recognize that this is an acid, but this is not really complete because the PO4 that I'm familiar with is PO4 3 minus. This is a phosphate ion. Okay, that is what we have there. And if for this, in order to have a neutral charge, is maybe what it's implying, it would actually be H3PO4, and this would be phosphoric acid. But nonetheless, let's assume that we're actually trying to solve H2PO4. So for this, we would actually first, I do recommend starting out with the phosphate ion. But instead of doing a phosphate ion, I'm going to do a theoretical one because based on this, we're dealing with a PO4 2 brightest. Okay. With that being said, let's just go through it. Phosphorus, okay, based on the periodic table, that is on the 15th column. So that's 5 electrons it can donate. Okay. So that would be 5. Oxygen is on the 16th column, so that's 6 electrons it can donate, but there's 4 of them, so that's 6 times 4, that's 24. And then we have 5 and 24, but then we have this 2 here. This right here, because it's a negative, it actually implies, or actually states, that this whole ion is getting 2 more electrons. Okay, so with that being said, we have 5 plus 24 plus 2. Okay, and we have a total of 31 electrons. Let's see if we can balance this out. So we'll put phosphorus in the middle because it's the only unique one, and we're going to try to get it to have 4 oxygens. So we have 1, 2, 3, 4 bonds so far. That would be oxygen, 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 oxygen. Okay, so let's start with the oxygens. Oxygen right now is sharing 1 of its 6 electrons. So 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And 2, 3, 4, 5, 6. And phosphorus, on the other hand, is right now sharing, just make sure I'm counting this correctly, it's sharing 4 of its 5. So we just have an extra one there. Okay? But now we have the 2 minus, okay? So that means we want to now add 2 more electrons. So it's going to add it to 2 oxygens to fill the octet rule. 1, 2. Okay? So that's what I've done there to balance it out. So now 2 oxygens have finished their octet rule, but there's still oxygens that are very incomplete. So, with this being said, we're going to what we're going to do here to get the PO4 2 minus, we're going to now, right now we're going to count how many unpaired electrons we have. We have 1, 2, 3. Okay? So, in order to be able to balance this out, we need to at least make one of the unpaired electrons bond appropriately. Okay? And they would actually come together to form a double bond. So if we redrew this, we now have phosphorus with the 2 oxygens, and this one here, okay? And then we have the double bond right here. Okay, then we have the oxygen with this one lone pair. All right, and that is what we have currently. But then we still have this one lone pair. This one unpaired electron, which is why PO4 2 minus, unfortunately, just doesn't work. The reason being is because the fact that that's why phosphate ion needs the PO4 3 minus. I just wanted to work through this to show you why this wouldn't balance out, is because as we've shown here, we have literally one unpaired electron. Okay, and the reason why I say this doesn't work is there's nowhere you can put this one unpaired electron to where this molecule itself isn't unstable to the max. So the why I've done this is because I do think that this right here is a typo, and we actually want to draw the Lewis structure of H2PO4 minus. The reason why I say that is because the fact that if you add in 2 hydrogens to PO4 3 minus, that's how you get 1 minus left. So this would be a hydrogen dihydrogen phosphate ion. That is what we should be solving here. So now let's go back to this, what we're drawing here. If now we're dealing with 3 minus, so we've added 3 electrons, we can actually complete this octet rule by adding the last one right there, okay? That's PO4 3 minus, okay? And so now with this being said, it's actually quite easier now to add the 2 hydrogens. Because remember, these hydrogens are protons, they're just H pluses. You can actually throw them specifically into any part that has a formal charge of -1. And the reason why I'm mentioning formal charge is because, as you can see, the hydrogen here, hydrogen plus, this thing already has a formal charge of +1. So it wouldn't just go to parts that are neutral, it would go to -1. Now, to be able to find out the formal charge, we look at things like phosphate, for example. Its natural state, it would be like that, okay? 2 electrons and 3 bonds. But these 2 electrons can actually serve as other bonds because it has an expanded octet rule. And as you compare to the phosphate here, it indeed has 5 bonds total. Oxygen, on the other hand, all right, is normal sense because it has 6 valence electrons. It's like that. 2 lone pairs and 2 bonds, which is what happens here. So that one has a formal charge of 0. But these 3 oxygens here, instead, they have 1 lone pair and 3 bonds. So in order to do that, they would have to gotten rid of the bond and add the lone pair. In order for that to happen, it needs to take a step into a negative formal charge. That is a -1 formal charge there for oxygen. So each of these 3 oxygens has -1 because they have 3 lone pairs and 1 valence electron. So that's where the hydrogens will go. It doesn't really matter where, but we know that 2 hydrogens, well, 1 each, will go into the part where it's -1 formal charge. So you'd have a hydrogen that sticks right there, and a hydrogen sticks right there, okay? And now we can redraw this correctly just with bonds to be able to write down the whole dihydrogen phosphate ion, okay? And I will stress it as a phosphate ion because, as we said, those 2 hydrogens will not cancel out the charge. Now, as you can see here, the ones that were attached to hydrogen now have a formal charge of 0 again because they have 2 lone pairs and 2 bonds, which will be the one described right there, okay? So now we've drawn the Lewis structure, and we did expand the octet on the phosphate ion, and that is how we were able to lower the formal charge because now the phosphate has 0, the oxygens all have 0, and the only one that doesn't have 0 would be this oxygen here, which has a formal charge right now of -1 because it has 3 lone pairs and 1 bond. And this thing can experience resonance because this formal charge of -1 could happen at this oxygen, which means the hydrogen would have gone over here, or could have happened here, which means the hydrogen could have gone over, which means this hydrogen could have gone over here as well. It's only in one spot though. So if I were to quickly rewrite this, the other resonance structures would look like PO, not this, yep, and then OH. In fact, this double bond here could actually even move through it. So this one could actually be no longer the double bond. It could be like this. This is just one example of a possible resonance structure. Because now our formal charge is on this oxygen here. Okay? The important thing though is that however you draw it, just make sure that you're not breaking any octet rules, except for the ones that can't have expanded octet rules, because that should be able to lead you to the answer. But we're just going to hide this one. This would be the Lewis structure of H2PO4 minus, and I will stress it's an ion. This is not a neutral molecule. It does have a charge. It does not have a net charge of 0. So as you can see here, the way they've drawn it, they have, this is actually going to be a as we discussed earlier, H3PO4, phosphoric acid. You can see that because we have 3 hydrogens and 4 oxygens. So this is H3PO4, okay? And then this is an expanded octet, and this right here, the B, is an octet that's not expanded. So what they did is that they shifted one of the bonds on the double bonds out to the oxygen, okay? So what they did was like this. This one is with the hydrogen, and this is for H3PO4. So this is for phosphoric acid, okay? Which is why they have 3 hydrogens there. But the reason why they were able to do now that is because, as you can see, phosphorus went from 5, or actually technically if we redrew it as 2 lone pairs and 3 bonds, it went from that to 4 bonds, okay? And when you replace a lone pair with a bond, now you're going the opposite way, as it's no longer now you're adding an electron, you're taking it away. So this formal charge is actually a +1. And you can see here how we have now a +1 -1. And also the cool thing is that this still, for phosphoric acid, still has a neutrality, a net of 0. It is still going to be a possible form of phosphoric acid. It's just more unstable because, as you can see here, there is more of the formal charges that are not equal to 0. In fact, if I went ahead to now try the dihydrogen phosphate, which is what we were solving, the H2PO4, we would actually have like this, where we'd have a -1 here as well. This still would be in total H2PO4 minus, as we discussed, but this right here is more unstable than the one over here. This is the most stable. The starred one is the most stable because here there's a lot more of the formal charges that are not equal to 0. These two should reorganize to where they would cancel out their formal charge. So that's why B, as seen in this picture, would actually be more unstable than A. Okay? And exactly as I said, the compound A is more favorable in this case. And as you can see, even in this answer here from my colleague, they did draw H3PO4 and not H2PO4. Because H3PO4 is the one that has a net charge of 0, but H2PO4, as I discussed, would be the minus, H2PO4 minus. So nonetheless, this is correct. All right, let's move on to question number 3.